I would like now to introduce to you our keynote speaker, Thomas Auer. We could not find anybody more suitable to have an answer for this and give us his insights into future cities.
I'm not so sure if we have all the answers of what's the future of the city going to be alike, but I think we have some ideas, some guidance where things need to go. I mean, there are still people who doubt global warming. I mean, this image is the last proof. I mean, there should be no question anymore. Now let's talk about what does it mean and who are we? Like, I'm with Transsolar, an engineering firm from Germany with offices in Stuttgart, Munich, Paris and New York, still a very small company of about 50-ish engineers. And I'm also teaching professor at the TUM in Munich. And so our work is about, we call it climate engineering, whether it's in practice or in research. And what is climate engineering? What does it mean? We got invited in 2010 to do an installation at the Architecture Biennale in Venice. And we had this idea to do an indoor cloud. Now, a cloud, we thought, is basically the visualization of climate engineering. Can we manipulate climate to an extent that a cloud starts to appear? And that was the idea, and here you see the principle, the physics behind it. It's, in order to get a cloud, you need a layer of saturated air, you need a layer of 100% humidity. And when you have 100% humidity, you can spray in water, and then the water particles start to appear as a cloud. You do not see humidity in there, you see only water particles. And in order to make this cloud float, warm and humid air goes up, you need a layer of cold air which is below. And in order to avoid that the cloud layer is touching the ceiling, you need a hot and dry layer above. And so then you get this sandwich. It sounds very straightforward and very simple. Took us actually a couple of months of testing until we achieved these very stable layers. And then Tetsuo Kondo, an architect from Japan, he designed the space, he designed the ramp where people could walk through the different climate zones, basically going into a tropical, and then on top of the cloud there was more like a desert climate, hot and dry, and experience the different climates, experience the cloud from below and above. Now I show this is not our profession, we are not cloud makers, but would be fun, so. But it just shows to what extent we are really able to manipulate climate locally. Usually you try to avoid to get cloud in buildings, but we use this knowledge to create local comfort where people are. I mean, that's the basic idea behind it. And this year, the curator of the Biennale this year, Alejandro Arevana, when he talked about Transsolar, he said cutting edge engineering at the service of common sense. I really like this sentence because this is what it's about. It's about common sense. In a certain way, we lost common sense in building design. We had so much common sense over century, developed by trial and error. And we see it as our responsibility to a certain extent to get this common sense back into building design. We are living in a time where you have to prove things. That's why we do a lot of computer simulations, putting numbers to common sense. But if the society needs those numbers, we can certainly help it. But this is what it's about. Now, it's not only about energy. I mean, we heard about carbon emissions and global warming, but it's also about environmental quality. And I like to show this image, which we saw in a magazine. It was an advertisement for a water park in Tokyo, where it said, "Welcome to the breathtaking Tokyo water park, where you can wash away the pressure and stress of the overcrowded city." There seems to be a different sense of overcrowded in Tokyo. But I think what it shows to me is it doesn't matter how much energy they use in this water park, the energy consumption per person is negligible. So we cannot disconnect environmental quality, architectural quality from minimizing the use of resources. If we design a zero-energy building, which is so ugly that people don't use it, it's a waste of resources. It's still a waste of resources. We use land, we use material, even if it doesn't use energy in operation. So it has to go together. We have to create better environments for people, and we have to get a better understanding what creates a better environment. I think this is the main task. And by the way, it has to be sustainable. So this is the task. This is the task we are facing. The European carbon roadmap stated, sorry, this was too fast, stated that we have to reduce carbon emissions from the building stock by 90% until 2050. This means that the building stock basically has to become carbon neutral. I mean, this is bold. I have actually, being in this business now for almost 25 years, I have no idea how we can achieve that. And we have to be aspirational, but we also have to be inspirational with what we do in order to convince people to get to where we have to get. But this is the task, and this is not an aim, this is legislation by the European Union. Now, we reduce the discussion right now to the question of insulation. And I mean, this sheep understands very well the value of insulation, but it's not as easy as this. I think we have to be much more holistic in our consideration. And in order to explain it, I have this simple chart from a friend, from Thomas Stark, who is professor in Constance. We always balance energy consumption per square meter. And he said, what if we do personalized energy balance and balance also commuting? And he used 3 typical persons. The first one is Mr. Miller, and he lives in a house with 200 square meters with 2 people. And Thomas is also from Stuttgart. That's why he has to use Mercedes as a reference. It's kind of mandatory. So he said he's using his C-Class Mercedes, like a middle-class car, and he's commuting 50 kilometers every day to work. So what's his personal balance? And then this is his personal balance. The red is heating the house. Yellow is basically appliances like computers, TV, screen, etc. And the gray piece on top is commuting. Now he compared it with Mr. Meyer, who lives in a passive house. So obviously the highest energy standard in housing, and he lives on only 160 square meters with 4 people. So only 40 square meters of building operation is dedicated to him, but he loves his SUV, he has an M-Class, and he is commuting 30 kilometers because you cannot build a single-family house in the city anymore. So he put it outside the city. He's commuting 30 kilometers every day with his SUV into the city, and then suddenly this is his balance. I mean, it's a very simple equation. The building doesn't matter anymore. It's his commuting which makes his personal balance. And then he compared it with Mr. Schmidt, who lives in an Art Nouveau building, an old flat, 130 square meters by himself, and he's biking 2 kilometers every day to work. So we always call him the green professor, probably at the TUM, living in Schwabing in Munich. But that's his personal balance. So it's even worse. But he could, let's say, he could fine-tune his balance by renting 1 room to a student. So then he would cut the red bar into half. So I think what I want to say is, if we make the balance more holistically, and if we take the whole lifestyle into account, if we start to personalize it, we get to a different perspective. We change the perspective and we start to recognize it's not only about insulation, it's much more. So this is what we have to do, and this is basically the 2000-watt society idea in Switzerland. To this regard, this society model in Switzerland is very valuable and very helpful to get a better understanding. So this was on a building scale and urban scale. The other thing is we get more frequent heat waves in Europe, all over the world, but also in Europe. And this is an image from Dubai, which someone from Foster Architect took. And you see this streetscape in Dubai, the picture with an infrared camera. And I mean, everybody of us know the situation. You walk over a 60, 70 degree hot tarmac in summer, and it's radiating into your face, and it starts to become unbearable. And this is what they did. I mean, with 40 degrees outside, the radiant temperature someone is facing is 52 degrees, plus he is exposed to the sun, so all of a sudden, this environment is unbearable for people. You can't go out of your air-conditioned car. And it's man-made, so what we need to recognize that in many areas of the world, in many areas in our city, we did whatever we can to make the situation as bad as possible, like here. So, I mean, and we saw this heat wave in 2003, and this is just a map which is in Wikipedia showing the delta to normal summer, and you see that France got hit the most, and the statistics said that in France about 15 people died due to the heat wave. And this is a statistic from Météo de France, which is very interesting, and it shows in this upper diagram, it shows the average summer temperature over the past 100 years had been within this band. And then all of a sudden, this was the summer of 2003, and then you see how temperature is going to go up over the next 100 years. And we recognize that the summer of 2003 is going to be a very normal summer in 2050, and the coldest summer they have in Paris in 2100. So we have to act, we have to change something if we want to avoid that we get air conditioners on every single window. And the problem what happened in Paris was a combination of this heat wave and urban heat island effect. It was not so much the urban heat island effect during the day, which was the problem. Météo de France measured during the day only 1 degree more at peak, as a peak temperature than they measured outside of Paris. But at nighttime, they measured 10 degrees more. So whereas the outside of Paris cooled down at nighttime to 20 degrees, downtown Paris stayed at nighttime at 30 degrees, and all our buildings without air conditioning, we heavily rely on cool nighttime temperatures so that with natural ventilation, we cool down the thermal mass of the building. And this didn't work anymore because the city didn't cool down at night. And then all of a sudden, they had 40, 45 degrees in the buildings. And then elderly people started to die. And so this is the requirement. We have to create livable cities. Of course, we have to create better environment. We need to talk about mitigation, minimizing carbon emissions. But we also have to talk about adaptation. How do we adapt our cities to achieve better, more resilient climate in our cities? And now, looking at some examples on a building scale, this is one of the nominees. This is but a pure coincidence. This is the building of Baumschlager Eberle on the left side, the 2226 in Lustenau, which might be, let's say, changing the perspective of building design. What they do, they build 80 centimeters, almost 75 centimeters thick walls to create as much thermal mass as possible to control the indoor climate and minimizing technology. So no heating, no cooling, no mechanical ventilation, no air conditioning, but supplemented with smart technology using sensors to sense air quality, which opens the motorized natural ventilation flaps. And then on the other side, it's the opposite. It's the building of Werner Sobeck. It's a research project. It's B10 in Stuttgart, which is all about high technology. You see the control panel, and it's basically supplemented with passive systems, with daylight and also some natural ventilation. So we see one building which is all about passive strategies, supplemented with some smart technology, and we see the other high-tech building which is all about high-tech supplemented with some passive system. Now the question is, what's better? What's the future going to be like? And I mean, I'm not so sure if I have my personal opinion. My personal opinion is that every building we did, which was too complex, never really worked. I mean, that's what we have to face. The more simple, the more robust buildings are. The more simple, people better understand how to operate. I mean, that's the lesson we have learned over the past 25 years, but I'm certainly not the person who say we're going to see a future without technology. I mean, we're not going to go back into caves. So the question will be, how can we maximize passive strategies and supplement it with smart technology where needed? But just as one statistic from a building where we worked on, which is in Canada, a high-rise building in Winnipeg in a very severe climate with winter temperatures of minus 35, summer temperatures of plus 35 degrees. But the reason I show this is we put radiant heating and cooling into the concrete slab. So it's all about thermal mass, which we activate, but it's a very extremely slow reacting system. If anybody complains it's too hot or too cold, it takes about a day to adjust temperature by something like 1 degree. So you basically don't even need to complain. Now, Manitoba Hydro, as a utility company, they operate all kinds of buildings, and they have something like 10 or 20 fully air-conditioned buildings. And as a Crown corporation, like as a public mission-driven company, they feel the responsibility to take the lessons learned from this building and publish it. So these are statistics published by Manitoba Hydro. We didn't come up with these statistics. And so in this upper diagram, they compared service calls for too hot and too cold with this building compared to the fully air-conditioned building. And the interesting and funny result is that we get half as many calls for too hot or too cold in a building where we have no temperature control compared to a building where we have instantaneous temperature control. I mean, I have some ideas what's the reason for it, but this is, first of all, strange and very unexpected. And then the second is we have 1.25 less sick days in this building with all maximizing passive systems, which they have in their fully air-conditioned building. I mean, these are two objective results of a building compared to others, and which we can't neglect. So talking about passive systems on buildings we worked on, this is the Damascus School, the French school in Damascus, where we had the fortunate situation to work with Atelier Lyon from Paris, architects from Paris. And it was the parents who approached us who said, can you do a building in Damascus without air conditioning? And so we studied the climate data. We saw that Damascus actually cools down at nighttime significantly. In summer, every day they have temperatures of 40, 45 degrees, but it cools down at nighttime to something like 20 degrees. And we said, how can we maximize this nighttime cooling? So what we did, we created these courtyards in between these two-story classroom buildings where we have some vegetation, some shading to create a nice microclimate. And we take the air from these courtyards and draw it through pipes which are embedded in the ground slab before the cold air is supplied into the space, and then we exhaust it by these solar chimneys. So hot air goes up. Now, if you have the sun heating up the exhaust air further, you keep this natural ventilation going. So there's no fan in the system, there's no mechanical unit, and then we have more pipes in the ground slab which supply air to the upper classroom, and it's also driven by the solar chimney. The solar chimney is exposed to the west so that we get the low sun angles in the afternoon, heating up this masonry wall on the backside, which is painted black. And so this wall stays hot overnight, and it keeps the system, it keeps the natural ventilation running at nighttime to cool down the floor slab, to cool down the thermal mass of the building. And by doing this, we achieve, now the question, what is comfort? We achieve, in my mind, highly comfortable conditions. So in our simulations, we showed that we can keep the indoor temperatures at the end of a hot period, at the end of the day, at temperatures of something like 30 to 31 degrees. And the parents said, 31 is fine at 45 outside. In the meantime, we have adaptive comfort standards where we can actually prove this, that it's really comfortable in those extreme conditions. And before this unfortunate civil war in Syria, the school wanted to extend the building using the same system again, which is for us always a proof that they really like the conditions they have. And then the other one is here in Europe, it's the Ricola Building in Switzerland by Herzog Demerer Architects. And Ricola, for their herb storage, they require very precise humidity. 50% relative humidity, plus minus 5%. And the most high-tech material we still have that is controlling humidity in an environment is rammed earth. So the idea was pretty clear early on that this should become a rammed earth building. And Martin Rauch from Austria, he built it finally. And here you see, I mean, there was a funny story that we couldn't put insulation into the rammed earth. So rammed earth is conducting humidity, but it's also conducting temperature very well. So we couldn't insulate it. And we did a life cycle analysis proving to the SIA, the Swiss Engineering and Architecture Association, that over a lifetime of 100 years, we are still better, even though we have higher heat losses, because we have basically no embodied energy to build this rammed earth wall. And so this is during construction, some images, and this is how it looks like. So, I mean, the point I want to make is we can use material, we can use form and material in architecture to control climate, to control daylight, to control natural ventilation, and to control our environment. And we have proven with many buildings that people appreciate this, let's say, passive approach where temperature change incrementally over the course of the day, appreciate it more than air conditioner, which have an instantaneous reaction on a space. Here's some more images. And to this regard, we really appreciate that it seems there is a new renaissance on using brick, using thermal mass in buildings as a materiality, but also we can use, this is all the nominees from the 50 nominees from the Brick Award, which we took from the website. But we also see this when we get on the bigger scale. The other issue I talked about, I mentioned, is urban climate and microclimate and comfort for people. This is interesting. When we talk about density, there's always this complaint that if we increase density, we increase urban heat island effect at the same time. It's true there is a relation between urban heat island effect and density, but there are more parameters. One of the parameters is, again, urban form and materiality. And I like to show Siena because Siena measured their urban climate and figured out that they have a negative urban heat island effect. At peak day conditions, the temperature in downtown Siena is cooler than it is outside of Siena. And I mean, that's interesting because you don't even see vegetation or other things to improve the climate. This is purely achieved by urban form materiality, shading, having thermal mass exposed to the public realm and trying to avoid that the thermal mass is exposed to the sun during the day. This is how this was achieved. And I mean, we just have to learn from those achievements and bring it back into building design. Here you see two streets, you see the self-shading effect of those narrow streets. Of course, this is a conflict with traffic. So you don't see much traffic here, and it has a reason. But this is something we need to debate, and this is something we need to negotiate. So we need to design public realm for better comfort, also for people, and it can be done better than in this plaza in Mexico City, where you see just some shade has so much improvement. Here, an example of Ecosistema Urbano in Madrid, where a shading structure combined with vegetation creates a cold spot in a city where people can gather, where people can meet. And then two projects we were involved. One is the Breathe Austria, the pavilion, the Austrian pavilion at the Expo in Milan. And it was about how can we create the performance, how do we get the performance of a forest onto a space of 560 square meters. How can we accelerate the performance of a forest by using fog and elevated air speeds to improve the performance and improve the climate? So this was the idea, the 3.1 hectare of forest, the performance we want to get onto 560 square meters. And it worked pretty well. So it's a question of mist, evaporative cooling that comes from the vegetation, that also comes from these fog systems, combined with some fans which create air movement. And so they started to program different climate zones as people walked through the pavilion and also experienced different conditions. This was the only pavilion, so thanks to Austria, this was the only pavilion on the Expo in Milan which was not air conditioned. Also the indoor, I mean this is outdoor, but they also had indoor spaces, so also the indoor spaces took the air from this microclimate and avoided air conditioning for the indoor spaces. And then the other one is the Place de la République in Paris, where we work with TVK architects. And here you see Place de la République before it got remodeled. It's about traffic. They had all this traffic going through Place de la République, but it's also about the color, the absorptance of the surfaces. And this is how Place de la République looked like after the remodeling. And you see with the bright surface, we get much less, we absorb much less solar energy during the day. It's much cooler during the day, but it also doesn't store this heat into the nighttime. So it's changing the physics, it's changing comfort in this area surrounded by Place de la République. It doesn't change the climate in Paris, obviously, but it's just an indicator of what we need to do. So it's not about rocket science what we do here. It's just getting common sense back into building design and urbanism. Here are some images of Place de la République, how it looks today. And I really like this one. You see people enjoying this. And I think coming back to this question, what we need to do, we need to deal with these heat waves, creating more resilient environment. But we also have to use this to create better environments for people. So thank you very much.